Concrete is not inherently conductive to electricity. However, moisture and ions present in the concrete can create a conductive path. In a UFER grounding system, the rebar in the concrete foundation and the concrete itself serve as the grounding electrode. The concrete provides a conductive path between the rebar and the earth, assuming there is sufficient moisture and ion content in the concrete. In your specific scenario, the rebar in the wall is not directly connected to the rebar in the footer. This means that the concrete in the wall is the only path to ground for the rebar you intend to bond to. The adequacy of the ground depends on several factors. Firstly, the concrete must have sufficient moisture and ion content to provide a conductive path. Secondly, thicker concrete provides a better grounding path than thinner concrete. Thirdly, the longer the rebar is in contact with the concrete, the better the grounding path. Bonding to a horizontal rebar that is 8 inches above the bottom of the foundation may not provide a good ground if the concrete conductivity is low. However, it may still be sufficient if the concrete is sufficiently thick and moist. The rebar in a footer is not in direct contact with the earth either. However, it is typically located in the thickest and most conductive part of the concrete foundation, providing a better grounding path. In conclusion, the adequacy of the ground in this case depends on the specific conditions of the concrete. It is important to consider the factors mentioned above and consult with a qualified electrician to ensure a safe and effective grounding system. The National Electrical Code, or NEC, provides guidelines for grounding and bonding to ensure electrical safety. A UFER ground, also known as a concrete encased electrode, is a common method for providing a low impedance path to ground. The NEC specifies requirements for the size and length of the rebar used in a UFER ground, as well as the minimum amount of concrete cover. When installing a UFER ground, it is important to ensure that the rebar is securely bonded to the grounding electrode conductor. This can be done using a listed connector or by welding the rebar to the conductor. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the ungrounded service conductors. In addition to the UFER ground, other grounding electrodes may be required, such as a ground rod or a ground ring. The NEC requires that all grounding electrodes be bonded together to form a grounding electrode system. This ensures that all parts of the electrical system are at the same potential, minimizing the risk of electrical shock. When evaluating the adequacy of a grounding system, it is important to consider the soil conditions. Soil resistivity can vary widely depending on the moisture content, temperature, and chemical composition of the soil. High soil resistivity can make it difficult to achieve a low impedance path to ground. In such cases, it may be necessary to use multiple grounding electrodes or to improve the soil conductivity by adding ground enhancement materials. It is also important to consider the potential for corrosion of the grounding electrodes. Corrosion can increase the resistance of the grounding system and reduce its effectiveness. To prevent corrosion, grounding electrodes should be made of corrosion-resistant materials such as copper or stainless steel. The NEC also requires that grounding electrodes be protected from physical damage. This can be done by installing them in a protected location or by using a protective sleeve. When working with concrete, it is important to be aware of its chemical properties. Concrete is a porous material that can absorb moisture and chemicals from the surrounding environment. This can affect the conductivity of the concrete and the performance of the grounding system. To minimize the effects of chemical contamination, it is important to use high-quality concrete and to protect the concrete from exposure to harmful chemicals. It is also important to ensure that the concrete is properly cured. Curing is the process of keeping the concrete moist for a period of time after it is poured. This allows the concrete to fully hydrate and develop its strength. Proper curing can improve the conductivity of the concrete and the performance of the grounding system. When installing electrical equipment in or on concrete, it is important to use appropriate mounting hardware. The hardware should be made of corrosion-resistant materials and should be designed to withstand the weight and vibration of the equipment. It is also important to ensure that the hardware is properly grounded. This can be done by bonding the hardware to the grounding electrode system. When working with electricity, it is important to follow all safety precautions. Always disconnect the power before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards of electricity and take steps to avoid them. If you are not qualified to work on electrical equipment, consult with a qualified electrician. A qualified electrician has the knowledge and experience to safely install and maintain electrical systems. They can also help you to ensure that your electrical system meets all applicable codes and regulations. The NEC is a complex document, and it can be difficult to understand all of its requirements. If you have any questions about the NEC, consult with a qualified electrician or electrical inspector. They can help you to interpret the code and to ensure that your electrical system is in compliance. Grounding and bonding are essential for electrical safety. A properly installed and maintained grounding system can protect people and property from electrical shock and fire. If you have any concerns about the safety of your electrical system, consult with a qualified electrician. They can inspect your system and make any necessary repairs or upgrades. Remember that concrete resistivity is affected by several factors. Firstly, moisture content plays a big role, as higher moisture leads to low resistivity. Secondly, the type of aggregate used in the concrete mix also influences conductivity. Thirdly, the presence of additives such as chloride salts can significantly increase conductivity, though this can also promote corrosion. Fourthly, temperature also affects resistivity, with low temperatures generally leading to higher resistivity. Therefore, when evaluating a concrete encased electrode, it's not just about the presence of concrete but also the specific conditions affecting its conductive properties. Consider using specialized concrete mixes with enhanced conductivity for UFER grounds in situations where optimal grounding performance is crucial. Also, regular inspection and testing of the grounding system are recommended to ensure its continued effectiveness. This is particularly important in environments with fluctuating moisture levels or potential for chemical contamination. The goal is to maintain a low impedance path to ground, which is essential for safety and proper operation of electrical equipment. Furthermore, proper documentation of the UFER ground installation, including details about the rebar size, concrete mix, and grounding conductor connection, is important for future reference and maintenance. This documentation can be valuable during inspections or when troubleshooting electrical issues. For large or complex structures, consider using multiple UFER grounds interconnected to create a more robust grounding system. This can help to distribute fault currents and minimize voltage gradients, further enhancing safety. In some cases, it may be necessary to supplement the UFER ground with other grounding electrodes such as ground rods or ground plates to achieve the desired grounding resistance. The choice of grounding electrode will depend on the specific site conditions and the requirements of the local electrical code. Also, be aware that the effectiveness of a UFER ground can be affected by the presence of underground utilities or other metallic structures. These structures can create unintended ground paths or interfere with the flow of fault currents. It is important to carefully plan the location of the UFER ground to avoid these potential issues. The NEC Section 250 covers grounding and bonding requirements in detail, including specific provisions for concrete encased electrodes. Consult this section of the NEC for guidance on proper installation and testing procedures. Also, remember to use listed and labeled grounding connectors and hardware to ensure reliable and safe connections. Avoid using dissimilar metals in the grounding system, as this can lead to corrosion and reduce performance. Finally, keep in mind that the information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrician or electrical engineer for specific recommendations regarding your grounding system. They can assess your particular situation and provide tailored solutions to meet your needs.